Thank you, Jacob. All right, and thank you all for being here. Hopefully in the break between the talk and the Q&A, I'll get the chance to actually see everybody who's here um, and figure that out. And apologies if I'm all flustered. I just discovered that my exciting new laptop, the camera isn't working. So this is on an older one, which is not going to be as nice, but should work fine. Okay. Wonderful to be here. Very excited to be speaking in front of this great audience. So today, what am I going to be going into, right? So I hoped, and it looks like it's true that people would turn out with some interest to talk about toy theories, even though there's a lot of kind of disparaging statements that get made about toy theories, that they're not philosophically interesting, that they're not scientifically interesting, especially. And I want to focus on a particular kind of definition of toy theories today, which is theories that have no empirical content in the sense that observation is physically impossible in those theories. I think if we look at things in an honest way, we'll realize that a very large number of the theories that we interpret, and actually a very large number of the theories that we use in practice to help predict experimental data, are toy theories in this sense. So the main kind of tension and question that I want to look at is that when we're looking at interpretation of symmetry, right, and trying to apply a principle that I think is plausible, which is the principle that symmetry invariant quantities are the ones that are physically real and non-invariant quantities aren't real, right? I think this is at least a way that we should prefer to interpret our theories. It's kind of an epistemic norm on our choice of interpretation of scientific theories. And this can lead to some puzzles. And I think in the case of toy theories, it leads to a very serious puzzle about what it could mean to interpret a toy theory, right? So I'm going to look at some examples of the interpretation of symmetries in toy theories that come up from Gordon Belot, his famous didactic rant on symmetry and equivalence. And those are going to lead us to the question of how to interpret toy theories in general. As I was kind of just alluding to, I think toy theories are pretty widespread and often treated as very important. Some of them are even used in a kind of roundabout way to predict experimental data when you're conducting idealizations of some sorts. And the problem is that what I consider the most plausible accounts of what we're doing when we interpret theories in an ordinary way don't apply to toy theories. So the goal is to kind of resolve these tensions and along the way, solve the puzzle about the symmetry to reality inference that's going to arise from Belot's work. I'll, explain when we get to Belot's work exactly what that puzzle is. Okay. So here is a principle that I am committed to, right? I'm not committed to it in the sense that I think, come hell or high water, this is how we should interpret theories, but I think it's a kind of, other things being equal, epistemic principle of interpreting theories, which is solutions related by dynamical symmetries should be treated as physically equivalent. Again, ceteris paribus, at least they should be treated as physically equivalent, right? If you have an otherwise good interpretation available on which you're treating solutions related by symmetries as physically equivalent, you should do so. And there's a number of justifications that can be given for this. A bunch of people, Shamik Dasgupta has given the most kind of precise and trenchant defense of this principle on the basis of Occam's razor, which is that if we can avoid drawing distinctions between states, we should do so. It makes our overall picture of the world simpler. There are a bunch of other defenses that one can give. Jill North's matching principle, the idea that the structure of a theory should mirror the structure revealed by the dynamical laws, right? There's a bunch of other justifications for this. And I think actually multiple of these justifications are pretty good. And I subscribe to several of these arguments in favor of symmetry reality inference, which is one of the reasons why I'm so committed to it as a principle. At any rate, I want to defend this as a norm on the interpretation of physical theories that should be followed whenever possible, right? And, you know, it isn't always going to be possible. Sometimes you won't have a satisfactory invariant version of a theory that can be put forward, but when you can, you should. So with that in mind, Belot has put forward an attack on symmetry to reality inference from a number of really compelling examples, some of which are much less idealized than the ones I'm going to talk about now. But my interest today is in some of his more idealized examples, because I think they're super interesting, and some puzzles arise from these idealized examples that don't arise as much from the less idealized ones. But Belot lists a number of examples of theories that become absurd when we apply the symmetry to reality inference principle. So one example he gives is the symmetry of the Kepler problem. You know, like you have a central force, there are objects orbiting that central force under just the influence of gravity, right? Equal areas swept out in equal times. Those kind of that being the idea is that the most fundamental law of the theory is Kepler's law. So in that model, it has, in addition to kind of the usual symmetries of Newtonian gravity, it has this kind of goofy symmetry called the Runge-Lentz symmetry, which is associated with the conservation of the Runge-Lentz vector. And this symmetry just doesn't leave relative distances between the force, the central force, and the orbiting body, the planet, maybe. It doesn't leave that invariant, right? So I have a little image there which shows actually a pretty mild case of how different two orbits can be and be related by the Runge-Lentz symmetry. And of course, you can see that the distance of closest approach between the sun, which is at the center of my little coordinate system there, my little like MS Paint coordinate system, and the planet is going to change when you apply the symmetry. So that looks pretty weird, right? It looks like you're talking about a theory that doesn't even have relative distances defined if you apply this principle of symmetry to reality inference. And, you know, Belot's thought is, well, this is kind of a reductio ad absurdum of the principle. And another example, Belot actually talks about a wider class of symmetries, but he's going to get into dialogue with Wallace, who just talks about the conformal ones. So I'm going to talk about the conformal ones. But if you take vacuum electrodynamics, right, the theory has a conformal symmetry, which again doesn't leave distances invariant, right? Only angles. And you might think that this is a pretty absurd view, that you should interpret electrodynamics. Again, when I say vacuum, I mean electrodynamics, not again, I haven't said this yet, but when I say vacuum electrodynamics, I mean electrodynamics in the absence of charges, right? So this theory has a conformal symmetry. And so you would think, well, wavelength, for example, isn't a real quantity according to that theory. And that's pretty bizarre, right? We should think of wavelength as being one of the basic kind of things, not the most basic perhaps, but a real quantity at least when we're describing electromagnetic waves. So Belot's conclusion that he draws from this is that symmetry to reality inference is not really a viable principle because it leads to these kinds of absurd cases, right? Of course, one thing to note is that if you see the principle as kind of a ceteris paribus principle, the way that Dasgupta has talked about it, or the way that I've come to see it, I used to be much more absolutist about it, but now I think of it as a ceteris paribus principle. Then you'll think, well, okay, maybe these examples are examples of the small number of cases where it breaks down and where other factors outweigh the importance of symmetry inference. But maybe we have some better options. So in particular, David Wallace has responded to these examples of Belot's. Now, Wallace is asking a somewhat different question. He's not asking about which quantities we should understand as physically significant when we're interpreting the theory. In this passage, he's talking about which quantities are observable. But I think that the points that he's making are ones that would port over to the interpretation question. And the fact that he's engaging with Belot here, I think indicates that he agrees with that, right? At least, he thinks that these points should count against Belot's points about whether these quantities are observable. But then, of course, like if they're observable, then they must be physically significant. So Wallace is going to, I think, take this argument to defend the view that we can apply symmetry to reality inference, perhaps, to this kind of example, while holding on to the idea that the quantities that aren't invariant under these funny symmetries, the Runge-Lentz symmetry and the conformal symmetry of vacuum electrodynamics, that those quantities that aren't invariant under those symmetries are still real. How does he do that? Well, he says, look, these symmetries are kind of idealized symmetries that only show up under special initial conditions, right? And furthermore, these special initial conditions are non-physical in the sense that they don't allow for measurement. So once we kind of do something to permit measurement, once we make kind of a minimal change to the state that would be required to allow for measurement, these symmetries are going to go away. So here, talking about the case of the conformal symmetry in electrodynamics, he says, well, the unobservability thesis would seem to imply, remember, like, one thing to note is Belot does have to say no to Wallace's unobservability thesis to hold on to what he's saying in his chapter. So I think that's one of the reasons why Wallace is kind of engaging with him here. Wallace says, it would seem to imply that radiation frequency is undetectable, since, again, frequency isn't invariant under conformal transformations, so that no observation can distinguish visible light from X-rays. This is obviously absurd, but it's obvious why this is absurd, because the conformal symmetry is only a symmetry of radiation in the absence of matter and ceases to be a symmetry of systems in which matter is present, right? So once we introduce matter, which is required in order to detect the radiation, the conformal symmetry goes away. So in this really insightful paper, right, Wallace points out that for these purposes having to do with observability, we need to ask if the symmetry remains when an external measuring device interacts with the system, right? So now I'm going to do something which probably amounts a little bit to straw manning Wallace, which I apologize for. The reason I'm doing it is because it helps the dialectic here. But I want to be clear that Wallace isn't committed to the views that I'm ascribing him to, or to him rather. But what I'm going to do is I'm going to pretend that what Wallace is doing here is also defending symmetry to reality inference on the basis of the same argument, right? I don't know that he would subscribe to that further kind of commitment, but I'm going to see what happens if we interpret him this way. So within that kind of dialectic that Belot started, suppose that Wallace also uses his argument to try to defend symmetry reality inference, right? So we need to ask what would happen if we introduce a detector into the system. And we should only treat a symmetry as relating physically equivalent states if the symmetry remains when we introduce measurement devices into the model. So one thing to say here then is that involves changing the subject, right? So Belot's question was about the interpretation of vacuum electrodynamics. And considered as a toy theory, right? There's nothing wrong with saying, it seems to me, we have a theory, I'm positing a theory that's exactly like ordinary electrodynamics that we use to predict all kinds of electric and magnetic phenomena, except that now we're saying it's physically impossible for charges to exist, right? Everything else is the same, perhaps, but we're saying it's physically impossible for electric charge to exist. That could be a theory, right? it's a toy theory in the sense that we'll talk about in a minute, but spoiler alert, so is electrodynamics itself if we're talking about classical electrodynamics. Okay, so if we construe or try to construe Wallace's response as a defense of symmetry to reality inference, it has to require kind of changing the subject away from the theory that Belot was talking about interpreting. And if symmetry to reality inference is supposed to be a norm on interpreting theories, period, then a counterexample is a counterexample. Second point, even when we introduce charge matter into the system, that's not really enough to get us measuring devices in any sense that we would think of as physically realistic, right? So a pretty famous trait of classical electrodynamics, I mean, not famous in the sense that like, I actually didn't know about this until I started doing grad school in philosophy of physics, but it's, once you see it, right? Bulk matter isn't stable in that theory. Once you get, you can have a charged matter kind of a piece of charged matter kind of orbiting another piece of charged matter, but it's highly unstable. And that requires particles, which kind of create, as Matthias Frisch has discussed in his work at, in really interesting ways. Charged particles also create possible inconsistencies in the theory. And the way to solve that is to talk about continuous charge matter. But then continuous charge matter, if you don't have any other forces, it's not going to hold together. It's just going to puff out to infinity, as quickly as it can, right? So measuring devices aren't going to be physically possible in classical electrodynamics, even if we include charges. They're just not. The laws are going to entail that any matter larger than a single charged particle, if there are charged particles in the theory, which again introduces problems of its own, any matter bigger than a single charged particle is not going to be stable. So you really can't have, even by pretty loose definitions of measurement devices, something that can act as kind of like a minimal computer. There's no way that such an object could exist in classical electrodynamics, right? If we understand the theory as purely the theory of the electromagnetic force. Now we could take Wallace's principle, all the way to the standard model and say a symmetry is only real for purposes of interpreting a theory or for purposes of asking what's observable in a theory, which is, his original question. We could take his principle all the way to the standard model and say, look, only if a symmetry remains when we go to a theory that's really realistic enough to give us measuring devices, and maybe the standard model is like that, right? If we take Wallace's principle all that way, then we could say, well, you can only treat symmetries as relating observably no different states or physically no different states if the symmetry remains when you go to a theory that is complicated enough and interesting enough and non-trivial enough to have stable bulk matter and possible measuring devices, right? Which might require the standard model. But one thing to note is that, like almost, pretty much all, maybe Porter Williams is a consistent about taking this approach. But if so, Porter is the only one, right? Because even Wallace, for example, has worked on the question of how should we interpret pure Newtonian gravity in light of its symmetries, right? Pretty much all of us, none of us is innocent of working on theories in which material measuring devices seem to be impossible, right? Because Newtonian mechanics, I don't know of a proof of this, but it seems highly intuitive to me that Newtonian mechanics by itself with pure Newtonian gravity is going to, certainly you can't have like, if your requirement for measurement is to have intelligent beings around, those can't exist in a theory with pure gravity, I'm pretty confident. But I'm also, I think it's fairly likely, although I don't know of a proof, that some generic features of that theory will prohibit the existence of measurement devices. So I think the problem here runs pretty deep. it seems to me, you know, that once we ask the question of what it means to interpret physics, we're going to run into trouble with any theory that counts as a toy theory by the following definition, right? So my definition of a toy theory, as I said before, to repeat, is a theory in which observation is physically impossible, right? So maybe a theory in which measuring devices or devices for the recording of measurements like computers physically can't exist. And I would, like I said, I would consider it a sufficient condition for being a toy theory that bulk matter is unstable, which is the case for a lot of classical theories. And showing that it's not the case in quantum theories is pretty non-trivial, as shown in the work of Elliott Lieb. Okay. Now, what are we doing when we interpret physics, right? So this is a problem that some people occasionally kind of say things about, but I don't think that philosophers of physics do enough kind of looking in the mirror and asking what it is that we're doing when we interpret theories. So there's this classic quote of von Frostens that gets cited from time to time, asking, well, when we interpret a theory, as von Frosten puts it with his characteristic use of little bits of French, he says, the interpretive question par excellence is, how could the theory be true, right? What are the conditions under which the theory could be true? Now, I think this question is, either turns theory interpretation into something quite question begging against what we would ordinarily think of as alternative interpretations, or it's just kind of like too content free to be helpful. So one thing to ask about this definition of von Frostens is, it's not super clear to me what it even means in quantum mechanics, for example, right? So quantum mechanics is kind of like there's a mathematical theory. There's a framework that you get from that for predicting experiments. And then in order to come up with an interpretation according to which that framework for predicting experiments is right, there's a pretty decent argument to be made that you might need to abandon the mathematical theory that you were using to generate that algorithm, right? Of course, like if you're an Everettian, if you're a many worlds interpretation person, or a quantum Bayesian or something like that, you don't think that anything needs to be changed about the formalism. But there's an open question, at least in the interpretation of quantum mechanics, about whether something needs to be changed about the formalism in order to get the experimental results right. And many people would say that something does need to change. So I think that this question of von Frostens is a little too narrow, for one thing, to encompass a lot of what just is the practice of interpreting theories like quantum mechanics. And the second thing to note about it is that it's telling us, yeah, something about like what we're saying when we say, here's an interpretation of a theory. But of course, when we interpret physics, a lot of the time what we're doing is we're asking like, what's a good interpretation, right? What's my interpretation? And people are often too, hardcore about this and say like, I advocate this interpretation, rather than saying like, for example, like, what's your degree of confidence in different interpretations, which would be my preference, right? But the point is, one of the things we're doing when we interpret physics is we're asking, how confident should we be in different interpretations, right? What are the epistemic norms on choosing interpretations? Now, von Frosten would have a problem with that, right, in a certain sense. But I don't think his reasons for having a problem with it are especially good. And anyway, the rest of us who want to ask what's the best interpretation aren't going to get, any help in that endeavor from this definition of von Frostens about what we're doing. So I was glad to see that Kevin Coffey's here, because Kevin has a great definition of what it is to interpret a theory. I don't remember which of his papers this is from, but the idea is, when we interpret a theory, we're asking, what should we believe about reality under the assumption that the theory was empirically adequate, right? So I like this. This does a great job, for example, of capturing what it is that we're doing when we interpret quantum mechanics, right? We're asking, suppose that the quantum algorithm for figuring out, which experimental predictions are correct, suppose that that's the right algorithm. well, what would be a picture of reality that recaptures that algorithm, right, and predicts it, and what would be the most reasonable interpretation that meets that empirical criterion to accept. Okay, so I like this one. It gives us a nice epistemic norm on choosing interpretations. But the problem is there's no way to apply it to toy theories, because toy theories, by definition, can't be empirically adequate, right? They can't have measuring devices. Measurement is physically impossible in them. So there's no such thing as empirical data coming from a toy theory, if we're speaking strictly accurately. Big problem, I think. Now, here's the kind of grain of truth in those somewhat strawman-y interpretations of Wallace that I was talking about, right? Even the strawman version of Wallace contains a grain of truth, which is how you know that he's the greatest. So remember, right, my strawman Wallace was saying we should only apply the symmetry to reality inference principle when the symmetry is one that will be preserved, will be maintained when an external measuring device acts with the system or interacts with the system that we're talking about. And there's a grain of truth to this, which is a question we could be asking about a toy theory. Again, a toy theory by my definition, a theory in which observation is physically impossible. A question we could be asking is the following impure question about it. I say impure because it's not just a question about that one theory. It's a question about that theory with a kind of scaffolding of understanding of its use effectively in other theories, right? So the impure question is, how do we interpret this toy theory if we construe it as an approximate description of some aspects of the actual world, right? Some, but not all, you know. So for example, in Newtonian gravity, how do we interpret this theory if we understand it as a rough description of the motion of large objects that aren't moving, you know, large objects that aren't extremely dense, right? Aren't moving relative to each other at speeds that are anywhere near the speed of light, those kind of things, right? We could be asking that question about Newtonian gravity. Similarly, we could be asking the question about classical electrodynamics, you know, how do we interpret this theory understood as an approximate description of quantum electrodynamics at scales where the differences between QED and classical electrodynamics don't matter, right? So if we're asking that impure question, then I think Wallace's response to Belot is correct, right? Because the impure question is really a question about the toy theory understood as an approximation to some theory that isn't a toy theory and does include measurement devices, right? So then we can ask, in that more accurate theory, that more fundamental theory, what happens when we introduce systems that will actually work as measurement devices? And then we can kind of carry over that understanding to our interpretation of the toy theory, right? And that can help us to effectively identify what count as observables in the toy theory, right? They're not observables just in the toy theory itself, but they're observables in the toy theory if it's understood as an approximation to the non-toy theory, right? And on that reading, I think that Wallace's response to Belot is correct. Of course, that reading would require, if we were being truly precise, perhaps, to go all the way to the standard model with Wallace's principle. But, you know, I'll talk more about this. It wouldn't necessarily require that in every case. Answering the impure question, as I think I've just illustrated, it is going to require some work on the nature of approximation and on interpreting the more fundamental theories that the toy theory is supposed to be an approximation to, right? So it's going to be a big process. And, you know, to get back to something I said before, you know, I recommend Porter Williams's work for at least some initial pointing in this direction, right? We're going to need to potentially interpret, you know, if we're asking the question, people like Williams and Wallace talk a lot about the interesting question of interpretation is the question, what do we conclude about our world on the basis of these theories? If we are asking that question, then we're going to need to look at more fundamental theories as a way of interpreting and informing our less fundamental theories. I don't necessarily agree with him that that's the interesting question. I think it is the most interesting question, but I think it's the most interesting question by kind of like by a moderate margin, right? In the question of how do we actually interpret Newtonian gravity, period, by itself as a pure theory is also super interesting for a number of reasons. So suppose we're asking the pure question, right? I mean, the reason to ask the pure question, I think, is it's super interesting for one thing. What would have been a reasonable thing for Newton himself to think if he understood his theory fully, right? We might ask, does the pure question even make sense, right? Because as I was discussing, you know, there's this problem that comes from what looks to me to be the right definition of interpretation, Coffey's definition, that interpreting a toy theory just isn't going to work because it doesn't have any empirical content. But here are some reasons to try, right? Well, for one thing, it's a popular thing to do in philosophy of physics and in physics. There's plenty of work on space-time and Newtonian mechanics. And in physics, we can also find examples of people working on toy theories. Topological quantum field theories are, I think, one of the most philosophically interesting examples. So one of the ones that I'm most familiar with. Theorists in physics just do this all the time. In fact, when I was talking with Jacob about, in kind of the lead up to this talk, we spoke about some work on toy theories that he did when he was in graduate school. It's a very common practice, and physicists treat it as somewhat scientifically interesting, at least. Like, I would say they often treat it as very scientifically interesting. Most importantly, for my purposes, they treat these toy theories as having physical content, right? They don't treat them as not saying something, right? So I think the moral that we should take from that is that a theory can say something, can have content and be physically interpreted, even if observation is physically impossible in that theory. Furthermore, it's kind of hard to do without pure interpretation of theories that might count as toy theories, right? Because our current best theories, if we're going to ask the impure question about general relativity, for example, I think this is the clearest case. What is general relativity saying about our world? We're going to kind of have to ask the pure question about general relativity because we don't have the more fundamental theory yet. We know some of its features, perhaps, or we can guess. But to really precisely provide an interpretation of general relativity that answers the impure question, we're going to need to ask, what would a universe in which general relativity was exactly true be like? It seems to me. So here's one framework for what we could be doing when we're interpreting a toy theory. I call it the quasi-empirical framework, right? We could begin by specifying some quantities that in the real world correspond to observables or are similar, at least, to quantities that in the real world are observables. Relative distances, right? That's a good one. Position of charges, something like that, relative position of charges. So we begin by specifying some quantities like that, and then we interpret the theory as if those quantities were observable in accord with Coffey's maxim to say, what would be the best theory, with the following observations. Right now, there's a little bit of a tension here because I think it's going to turn out for a lot of these toy theories that, strictly speaking, it's impossible for their observational content to be captured by an ontology in which observation is physically possible. So you'll kind of have to do the best you can with banishing some inconsistencies here. And I think this is just a problem with approximation in general, right? There are very serious issues about how we define approximate truth and kind of like how we make logic work for approximate truth, right? Hopefully these problems will be solved in a couple hundred years, certainly not right now. But I think, I share the view that, for example, like Psillos expresses in his book on scientific realism, that our working concept of approximate truth can do a lot of useful work, even if it's not going to solve every conceptual problem about what approximate truth is like. Anyway, so we treat the theory as if these quantities were observable, right? Call these the observables of the toy theory. So for example, right, treat the field tensor in vacuum electromagnetism as if it were observable, which it is in the real world, right? Well, then you're not going to apply symmetry to reality equivalence, symmetry to reality inference rather, to the conformal symmetry of the theory, because, the field tensor is not going to be invariant under that. So this is going to be a key step in impure interpretation of the theory, right? If I want to come up with an interpretation of a toy theory that does a good job of capturing the way it approximates the real world, I'm going to want to apply this framework. So here's a second framework, though, and I think it's equally coherent, although maybe not useful in as many situations, but I think it's still useful in some physically interesting situations, in a certain sense of physically interesting. So we could start with a fixed partial interpretation of the theory. I'm borrowing this terminology from Ritchie's Interpreting Quantum Theories. We start out with a theory that has some content, right? So, for example, when we start out interpreting classical electrodynamics with charges, one of the things that doesn't change normally between interpretations of that theory is which parts of the mathematical formalism represent charge matter, right? Or matter with mass. These things are treated as kind of fixed constants of the interpretation of the theory. By analogy with that kind of example, we start with a fixed partial interpretation of the theory. The meanings of some quantities are already identified, right? We're not treating them as observable, but we're saying, I'm not going to consider interpretations in which this quantity has a different meaning than the one I've assigned to it, right? So Q represents charge matter, period. I'm not going to change that when I interpret the theory. Well, how do we settle on those fixed meanings that we start with? Well, I think it's settled by physicists' intentions in constructing the theory. They could also be tentative, right? It could be that once you start out with a fixed partial interpretation like this, you work with it, you realize, like this isn't getting anywhere. This maybe even there's some contradictions or tensions between the different posits that you made when coming up with the fixed partial interpretation. And you might want to alter that, right? So you could also relax that requirement and say that it's tentative and up for revision. At any rate, you start with a partial interpretation, and then you construct the most theoretically virtuous total interpretation of the theory, in which you're saying everything about what the theory is saying about reality, right? That's compatible with that initial partial interpretation, maybe with some revisions along the way if it turns out to be pathological, right? And when I say theoretically virtuous, there's a wide variety of virtues that could still apply in the case of a theory with no empirical content, right? It could be simple in the Occamist sense. An important one, which comes up a lot in these kind of examples, is maybe you could have one interpretation on which it has a well-posed initial value problem that gives you predictions about what the future is going to be like, whether probabilistic or not probabilistic, right? That can turn out to be a pretty difficult criterion to satisfy, actually. So apply those kind of norms to the construction of an interpretation. And here's a third framework, which is a pretty nihilistic framework, but it's one that I think arguments in favor are possible, right? There's a robust sense in which there is just no sense to be made of the best interpretation of a theory with no empirical content. Because remember, when we're asking about the interpretation of a theory, like what's the best interpretation of a theory, we're asking what's the kind of epistemically best interpretation, right? What's the one that you should be most confident of? What's the one that you should believe in if you think the theory is empirically adequate? Well, if the theory can't be empirically adequate, then another thing that's impossible is that some well-informed agent could believe the theory is empirically adequate and be looking for a good explanation of its empirical adequacy, right? For a theory like classical electrodynamics by itself, that can't happen unless the character we're thinking of is either misinformed or thinking of the theory as an approximation or a special case of some better theory, which isn't a toy theory, right? So we need to recognize this in a certain sense, like if we kind of apply complete logical rigor, we can't make sense of the idea of a best interpretation of a theory that has no empirical content. And as a result, maybe what we should retreat to is something more like, the idea that von Frosten perhaps has, just treat all interpretations that are compatible with the formalism as being epistemically on a par, right? You could also say, treat all interpretations that are compatible with physicists' intentions in writing up the theory as epistemically on a par. So that allows you to have a kind of fixed initial partial interpretation, right? So like, for example, you could say all the interpretations of classical electrodynamics on which Q represents charge and M represents mass are just epistemically on a par. There's no reason to prefer one to the other. There's an argument to be made for this. So which of these frameworks is kind of the right way to look at it? I mean, from the way I've been talking about it so far, you might have inferred this, but I'm pretty ecumenical about this, right? I think that all of these approaches have something going for them. And I think if we're careful about specifying which one we're doing, it's interesting to conduct all three types of interpretation on toy theories. So as epistemology is normally conceived, right, what should a reasonable being believe with this empirical data? The agnostic framework is well motivated, right? It couldn't be reasonable to believe a toy theory. And we should keep that in mind, right? We shouldn't paper over the fact that these theories don't have empirical content, and therefore it would never be reasonable to believe they were true in the strictest sense, unless you were misinformed about some things, right? Like maybe you haven't studied the theory fully enough to realize that bulk matter is unstable in the theory, right? But if you have a logically clear picture of the theory, you shouldn't believe that it's true. But there are some scientific activities which have scientific merit, such as coming up with thought experiments, right? Conducting a proof of concept for a kind of basic approach to theorizing, the way that we often do in quantum gravity theory. Or in a sense, like approximating a better theory is kind of like this, right? These scientific activities are what you might call quasi-epistemic. They have some analogies to what should you believe, but they're not asking what should you believe. They're asking what should you take some other non-belief attitude towards, right? What should you think about this theory other than believing it? So what about the uses of the virtue epistemic framework? Because we've already seen how the quasi-empirical framework can be useful, right? It can be useful when we're asking questions about how a toy theory approximates a non-toy theory. So the virtue epistemic framework, I think, is scientifically useful in lots of ways, as illustrated by the kind of examples that Jacob and I were talking about, working through thought experiments in somebody's research, right? The virtue epistemic framework is useful when you're conducting thought experiments or proofs of concept, right? If you're trying to say, well, look, can a theory of this sort exist, right? So for example, early in the program of constructive quantum field theory, they were asking, could you have a mathematically well-defined theory in which, the axioms of quantum field theory as precisely defined in the following way are combined with relativity, right? Could you have a theory like that that includes interactions? And it was a non-trivial question, right? And they eventually came up with some toy theories in 1, 2, and 3 space-time dimensions, I guess really just 2 and 3, that showed the existence of theories like that. And that was a pretty interesting achievement, I think. So for thought experiments or proofs of concept like that, we're looking for theories that resemble epistemically viable theories, right? It wouldn't be as interesting if you came up with a thought experiment. So for example, like one of the reasons why Newton's, like if you construe Newton's bucket thought experiment in the purest way, which like, I'm not, I'm the farthest thing that we're from a historian of physics. But when I teach undergraduates about the philosophy of space and time, a lot of the time what I do is say, just think about this bucket as being by itself, right? In a pretty much or entirely empty universe. Okay. Well, that thought experiment is interesting because it resembles epistemically viable models of gravitational phenomena, right? It has the same observable quantities as some theories that are epistemically viable, not toy theories, right? The viable theories that we're thinking of, by the way, might be unconceived of or in the works, right? So in the constructive quantum field theory example, at least these theorists would think of the standard model as being, in a sense, still in the works because there hasn't been a construction of the standard model on, Minkowski spacetime, right? We're looking for a theory that bears certain analogies to the standard model when we construct these proofs of concept, right? And the idea is these proofs of concept make it conceivable that the standard model could be a fully well-defined theory. Or, of course, this kind of thing happens in quantum gravity, as we'll talk about in a second. So for these purposes, for proof of concept purposes, we have reason to prefer virtuous toy models because a virtuous theory, a theory that's simpler, has a well-posed initial value problem, all that kind of thing, is more likely to be a good analogy to a theory that's going to work. So in the example of toy quantum gravity theories, right, physicists like John Baez and Steve Carlip have worked on 2-dimensional or 3-dimensional quantized vacuum general relativity with no mass in it as a proof of concept for dynamics that could change the topology of space-time, right? The interpretation of this theory isn't anything goes, right? These numbers, these vectors, these tensors could represent anything at all. No, it begins by analogies with 4-dimensional general relativity and by analogies to general relativity that has mass in it, right? But interestingly, as part of the methodology of this theory, only invariant quantities are treated by these theorists as quote unquote observables, right? So if you read their work, they'll say, well, the observables of the theory are all topological invariants. Of course, in the strictest sense of observation, it doesn't make sense to say, I think, like I can't come up at least with a mental model according to which observation devices, that is to say like stable bulk matter, could be constructed only out of topologically invariant quantities that don't care about distances or angles or anything like that. That seems impossible. I don't know, maybe it's not, but at least intuitively it seems very difficult to think of this. And they're not trying to model observers, but they talk about observables, right? I think what they mean by observables is physically significant quantities, right? So they seem to be using a form of symmetry to reality inference here. What this example, by the way, is just meant to illustrate is it's useful in the pursuit of quantum gravity to conduct proof of concept thought experiments, right? And you can get some nice ones by looking at theories that are analogous to, we might think, the theory that we're eventually looking for. And a reason to think that a theory is analogous to the theory that we're eventually looking for, we might say, is that it possesses epistemic virtues. if you had a theory that was completely ugly, and to return to my earlier example, didn't have a well-posed initial value problem, you would think, well, it's very unlikely that there would be any useful analogy between this theory and the ultimate theory of quantum gravity, because if the ultimate theory of quantum gravity doesn't have a well-posed initial value problem, we're screwed, right? We're looking for a theory that has this feature. So we want our toy model theories to have this feature. So that, the search for that feature should be a norm on the interpretation of toy models. What I think these points bring us towards is an ecumenical approach to the interpretation of toy theories. The quasi-empirical approach, where you say, look, here are some quantities that I'm going to treat as observable, as a brute stipulation. That's useful when we're trying to use one of these theories to approximate our actual reality, right? Or using them to approximate a non-toy theory that does have empirical predictions. But the virtue epistemic framework is useful when we're conducting thought experiments or proofs of concept, like the ones I was just talking about in quantum gravity, right? Ed Witten isn't using, Chern-Simons theory to function as an approximation to any real world experiments. No, what he wants to do is do some proof of concept work for certain general facts about certain theoretical frameworks that could hopefully be useful by way of analogy to the theory that he is trying to construct to eventually predict the right, results for experiments. On the other hand, if neither of these goals are being pursued, if I come up to you and I say, hey, like, here's my stupid theory, and you realize that that theory doesn't have stable bulk matter, or for some other reason, observation is impossible with in that theory, well, it's totally legit for you to then say to me, dude, you've given me a toy theory that isn't useful for approximating reality, and it isn't useful either for conducting thought experiments or proofs of concept. So what I'm going to say back to you is there's no sense in which one interpretation of this theory is better than another, right? If you're just giving me a pointless toy theory that isn't useful for empirical scientific pursuits or quasi-empirical scientific pursuits, then the agnostic framework is right, and you should be a kind of nihilist about the interpretation of that theory. To return
just a note, Dave, you have about 5 minutes.
Yes, thank you, Jacob.
No problem.
So to return to the question of Wallace versus Belot, well, on the quasi-empirical framework, right, which is effectively the one that Wallace is employing, there's no reason to expect all observables to be symmetry invariant when you are interpreting a toy theory, right? Because you might, and that's essentially what Wallace is pointing out, right? Because he's saying, look, the way that I might be interpreting vacuum electrodynamics is by stipulating that the quantities in vacuum electrodynamics that are observable in a more fundamental non-toy theory are going to be the ones I'm treating as observable there. So symmetry reality inference is not a principle that applies or applies at least with any generality when you're interpreting a toy theory on the quasi-empirical framework. But on the virtue epistemic framework, I think, as illustrated by that work in topological quantum field theories in quantum gravity, I think it is a pretty good principle, right? And so if we're talking about Kepler problem theory, the theory in which it's physically necessary that there are two objects and that one of them orbits the other, sweeping out equal areas in equal times, well, then we, I think, should, at least other things be equal, apply symmetry to reality inference and say, yeah, the invariants of this theory don't include relative position. And that's pretty weird, but that theory is also pretty remote from the real stuff that we're talking about. It might bear certain analogies to the real stuff that we're talking about, but I don't think this is a problem. This isn't a point against symmetry to reality inference for Kepler problem theory any more than it is in low dimensional quantum gravity theory. Yeah, like real life observables are not only topological invariants, but within this kind of perhaps interesting for some purposes toy framework, those are the physically significant quantities. And I think that's the same thing we should say about vacuum electrodynamics or Kepler problem theory. My bottom line here is the following. A lot of what philosophers of physics and physicists do is interpret toy theories. There's a lot of work about theories in which, strictly speaking, observation is impossible. Anything about classical electrodynamics, anything about pure Newtonian gravity, I think, is effectively interpreting a toy theory, right? The agnostic, quasi-empirical, and virtue epistemic frameworks each have their place, depending on whether these theories are interesting as approximations to real life systems, or whether they're interesting as analogies to real life systems in the case of thought experiments and proofs of concept. But, right, because my distinctions haven't been here so far, theorists haven't really always or often made clear which of these frameworks they're using. And so confusion can sometimes result, right? And I think that's effectively a bit of what's happening between Belot and Wallace, insofar as Wallace really intends to object to Belot, which again is an interesting question about the text in the case of Wallace. But confusion can result if one philosopher or one physicist is applying the quasi-empirical approach and another is implying the virtue epistemic approach. So I think the best thing to do when you're interpreting toy theories is to make clear in some way which of these frameworks you are using, or else you can get people talking past each other in some weird ways. That's what I have. Thank you very much for joining me for this.
Good. All right, Alyssa, nice to see you. You have the first hand. Please go ahead.
Okay, thank you. Nice to see you, Jacob and Dave. Thanks for the talk. It's really, really interesting. I'm sorry, I do have two questions, but I'll try to make them short and they're related. So like the first question is just, I feel like I see how by distinguishing these different approaches to interpretation, you do a good job of kind of tracking, or I mean, it was very convincing, like, what is the kind of explains the disagreement between Belot and Wallace. But I thought I was kind of feeling like you were wanting to do something more, which was to like defend why, like say in the context of the virtue epistemic framework, this symmetry inference is reasonable, like the symmetry to reality inference is reasonable. And I didn't see you, I guess I didn't see that. So I didn't know if you wanted to say something about that, like why it's reasonable in that case, also why it's not reasonable in the other case. So that was kind of my second question. So you say like, if you're taking the kind of quasi-empirical, what you call the quasi-empirical approach to interpretation, then there's no reason to expect that all the observables will be symmetry invariant. But then I guess my question was, well, what you're calling the quasi-empirical approach is the approach when you're trying to take the theory to approximate reality. So that, since you're saying we shouldn't expect the observables to be symmetry invariant there, that made me think you don't think like when you're trying to do ontology and figure out what the theory is saying about the world, that you should respect that symmetry inference, like that's a reasonable inference. But then I'm like, I don't know if, yeah, so was the reason why you were saying if you're taking the quasi-empirical approach, like maybe Wallace was there, you shouldn't respect that principle, is that because in order to interpret this toy theory as real, you have to make some false assumptions, and is that why that principle kind of isn't a useful kind of principle there? I hope that was coherent. I'm sorry.
No, it's totally coherent,
Okay,
Alyssa. And you're exactly right that this was kind of like, that ball was still more in the air than maybe it should have been at the end. Like, cause yeah, I also do think that the principle is still good. So what you're doing when you are using the quasi-empirical approach to ask an impure question about a toy theory, right? In order to succeed at that, you're going to need to apply the principle, but apply it to the symmetries of the more realistic theory that you're trying to approximate with the toy theory, right? And that's Wallace's point, essentially. Take the toy theory, but then think about which of that theory's symmetries are going to go away when the idealizations that you are applying go away, right? And there's a delicate question here, though, which I also haven't answered and have a less satisfying answer to, which is sometimes you're going to want to say that you're only asking kind of approximate questions about the metaphysics of the toy theory that you're talking about, right? So like, I might be trying to ask whether I'm a substantivalist on the basis of general relativity, right? While understanding in the back of my head that maybe I think it's likely that space-time will be reduced away in a more fundamental quantum gravity theory or something like that. So if I have that kind of approach in mind, I'm going to be asking something like, how good of an approximation is it to say that spatiotemporal quantities are among the most basic quantities, right? So in that kind of case, then I might use some symmetries that I know are going to go away at a more fundamental level, because I'm not asking the question about the fundamental level. I'm asking the question about the approximate level where the kind of toy or non-fundamental theory that I'm interpreting does apply, right? So there's that kind of question as well. But I think it's clear that in the kind of case that Belot and Wallace are arguing about, that the domain in which electrodynamics is happening with no matter at all is not the kind of interesting domain that Wallace is thinking of as the one to be interpreted, right? So in that sense, I think he's kind of making the right move for the way that he's construing the debate. Again, within my framework, which is not his framework, and I don't mean to impute to him the way of looking at things that I'm looking at things, but from the way I'm looking at things, what he's doing makes a good sort of sense. I hope that's helpful.
Yeah, that's really helpful. Thank you.
Alyssa, do you want to raise your hand again and go to the end of the queue? You said you had another question.
Oh, I asked both my questions.
Oh, you was both.
The first
Okay,
one,
good.
I guess, Dave, you addressed more the second. I mean, the first was, I mean, I guess you kind of implicitly answered. My first question was that, well, I don't know. You didn't really give a justification for the principle, but you were, I guess you had said in the beginning of the talk, you were saying like, you think other people like Shamik and Jill gave good arguments in defense of this principle. I guess I got confused because it sounded like you were only saying in the context where we're looking at theories as like proof of concepts or something like that the principle works. But no, you're thinking it works in general. It's just when we're doing this quasi-empirical approach, we're invoking idealizations, or we're only trying to describe approximate parts of the theory. And in those cases, you don't use the principle for that. That was the idea.
That's exactly right. And thank you for saying that, Alyssa.
Okay, thanks.
Because that was exactly what I was going to say if you left the question there. So that's perfect. Thank you.
Okay, great. Awesome. Thank you so much, Dave. That's really, it's been awesome. Thanks,
Alyssa. Kevin, you're next.
Thanks, Dave. So like Alyssa, I really enjoyed the talk. So one of the sort of interpretive questions that was in the background when I was trying to think this through was the sort of historical debate that the Newtonians had about the nature of the gravitational force. And the thought, part of what was, and maybe I was unsuccessful in doing this, but part of what was motivating my way of thinking about this question was that we should be able to sort of we should be able to pose that sort of interpretive question, but think it through using sort of more modern tools or a more modern understanding of Newtonian mechanics. And so what I was trying to do was sort of come up with a way of thinking about interpretation on which the sort of, in sort of, very, very simplistic terms, sort of, if you were a Newtonian at the time, but sort of had the sort of a modern understanding of Newtonian mechanics, what would have been the best way of interpreting Newtonian mechanics, right? And I guess I sort of wonder whether or not that question on the sort of the rubric you put forward, whether or not how you would understand that question, or whether or not that question even makes sense. Because certainly sort of, the way Wallace wants to understand these sort of questions about how to interpret Newtonian mechanics, it's clearly linked to sort of modern physics, where, whereas the sort of historical, the interpretive question that Newtonians were asking can't have been, connected. And so I'm curious whether or not you think that there's room for that sort of interpretive question in the rubric that you put forward, or how you would understand that, or what your thoughts were on trying to make sense of that historical interpretive question.
Yeah, good. Good. There is room, and I've thought about this because, like, it didn't make it into the talk, but I think that the kind of the way you're thinking about it is super interesting, and like one of the reasons why I don't subscribe to the kind of thing that Wallace will sometimes say, that says that the only interesting question to be asked is the question about like what is going on in our world and what can we infer about our world from these theories, right? So yeah, what I would say in that kind of case is going on is let's call the right thinking Newtonian the person who's thinking about Newtonian mechanics in a kind of modern way, but asking it from the kind of empirical perspective that they had then, right? So I think the right thinking Newtonian would think that what they're doing when they're talking about Newtonian gravitation theory is applying the quasi-empirical framework to a theory that is idealizing in a particular way, namely by omitting non-gravitational forces, right? So, if we're thinking about Newtonian mechanics, so if I recall right, the way that you think of it is like Newtonian mechanics is this framework that you can like plug in forces to, right? So thinking about it in that kind of framework way, then I think Newtonian mechanics understood that way by the right thinking Newtonian isn't a toy theory at all, right? But Newtonian gravitation understood as a kind of total theory by the right thinking Newtonian is a toy theory. And they should think of it in a quasi-empirical way as like, what should we conclude on the basis of this idealization where we dispense with all the forces except for gravitation?
Okay. Yeah. Okay, that's helpful. Thank you.
Great, thanks. So I have Jerry, you're next. And yeah.
Thanks, Jacob. Thanks, Dave, for the talk. I really like this ecumenical landscape at the close here. I wanted to ask about the characterization of toy theories as theories where measurement is impossible. I found a little bit uncomfy with this characterization because I feel like I want to say, for example, in quantum measurement theory, if you introduce like a brute ancilla where the macroscopic degrees of freedom get entangled with the right basis, and those macroscopic degrees of freedom are black boxed, but could be filled in later. Like I feel like I kind of want to say that's like a toy theory of measurement, and then like decoherence is maybe de-idealizing that further. But I'm curious how you would talk about this example, and also like how you think it fits into the dialectic, because especially after your dialogue with Alyssa, I have a better sense of how it could fit into the dialectic harmoniously, but I'm still not quite all the way there.
Yeah, thanks. Good. Yeah, I mean, maybe a qualification that I should have mentioned or flagged is that like I don't intend my kind of technical use of the term toy theory to like coincide exactly with the colloquial use of it or the kind of ordinary physics use of it, right? And I certainly would agree that a kind of like a partial model of observation of that sort would be a toy theory in the kind of ordinary language sense, just maybe not a toy theory in my sense. It would depend on whether a theory like that kind of has a available interpretation as, on the kind of false hypothesis, the false working hypothesis that it is a fundamental theory, right? So like, if it's kind of built into the fixed partial interpretation of the theory that some of the degrees of freedom are talking about macroscopic measuring devices, right? That's kind of like one of the things that you're not going to treat as negotiable in interpreting the theory. Then that theory is not really going to have a tenable interpretation where it's completely fundamental, right? Unlike most of the theories that we kind of work with in philosophy of physics, it's just not going to have that kind of that possibility for interpreting it that way. And if it doesn't, then I mean, for one thing, like that kind of puts it to some extent like a little bit outside of the framework that I'm applying here, because the framework that I'm using here is kind of like a framework that's about what are the most basic degrees of freedom in the theory, and what do those mean kind of ontologically. And it's not going to be I mean, you could definitely generalize the framework to include theories like that, but it's a little bit artificial to do so, if you see what I mean. So yeah, I guess I kind of think of theories like that as a little bit outside of the questions that I'm asking. Thanks.
Thanks, Jer. If it's all right, I have a follow-up to Jer's question. So how do you think about a theory like ADS-CFT, right? So we don't right now think that our universe has asymptotically anti-de Sitter boundary conditions. So ADS-CFT is usually regarded as a very powerful toy model, right? A toy theory where we have a lot of mathematical control that we don't have in more realistic space-time theories. And we certainly don't have enough mathematical control to be able to answer definitively whether ADS-CFT can accommodate observers, but it's also not obvious that it cannot accommodate observers, right? ADS-CFT doesn't assume the universe is ADS everywhere, just that it has ADS asymptotic boundary conditions. Way in the bulk, for all we know, there's complicated physics and observers are possible. ADS-CFT is usually regarded as a really powerful exploratory tool for just going in and looking for phenomena that would be difficult to construct otherwise. So I think it's widely viewed as a toy theory sort of par excellence. And I'm just wondering how you think of that with your definition. I know your definition is, as you said to Jer, you're not necessarily using the toy theory definition the way that it's used. But I feel like ADS-CFT is a pretty important example. So I'm just wondering how you accommodate that in your framework.
Yeah, right. So definitely a theory that is a toy theory per the kind of ordinary usage. And as you note, it's up in the air whether it's a toy theory by my lights, because we don't have results about whether observation can be modeled in that theory. Yeah. So that's right. So like, the thing to note here is, and I return to my slide about the virtue epistemic framework and its kind of role in proof of concept for this reason. It doesn't follow from my account of what a good theory for purposes of proof of concept or thought experiment is that it needs to be a toy theory, right? It often will. And for some toy theories, the way they get their content, the way that it becomes non-trivial, how we should interpret them, is because they're being used in a proof of concept or a thought experiment. But there's no law that says that all the theories that are used in proof of concept or thought experiment need to be toy theories, right? So I think what I'm calling the virtue epistemic framework could also be applied to the interpretation of theories that aren't toy theories. And, you know, for those theories, if you have a theory that's not a toy theory that does permit the modeling of observers, but you're not using it to model observers or not to model like anything like real world observers, you're using it as a proof of concept for something that you'd like to do with a theory that's more realistic eventually and could model something like real world observers, then I would again think you should use something like this virtue epistemic framework as your guide, even though what you're doing isn't a toy theory actually. So in that sense, like some of the norms that I'm talking about for the interpretation of toy theories can apply beyond the boundaries of the category of toy theory. And maybe this gets to something that would be, you know, a little more of a substantive answer to Jer's question too, because, you know, where theories don't count as toy theories by my definition, but are being used for thought experiments or proofs of concept, then I think a bunch of the norms that I'm talking about on interpretation of toy theories are going to apply to those theories too, even though they don't count as toy theories, because they're being used for purposes that we often use theories that are toy by my definition.
Thanks. I see we have a question in the chat. Noel, is it all right if I read this question in the chat? Okay, thanks. So the question is, how could you approach methodologically in framework of presented conceptual schemes to quasi-classical explanation of quantum mechanics in framework of classical theories as presented? And there's a link. Otherwise, saying, how could you reject or accept the presented scheme trying to explain quantum mechanics? Sorry for a bit too concrete question. Is that clear?
Okay, so
Christoph, do you feel comfortable describing your question?
Well, yes, sure. So the question is, so you have somehow accepted three alternatives views on toy models. And in my view, this paper is kind of representing a kind of promising toy model. So the question is, how could you methodologically approach this this presented paper in reference to your methodology that you gave to us today?
yeah, interesting. Well, I haven't read the paper. So it look
okay.
yeah.
Essential idea is that basically many people assign extra features to quantum mechanics that are a kind of only unique for a quantum mechanics, like quantum entanglement and path trajectory approach and so on, so on. But many other people used to say that a lot of analogies with quantum mechanics are kind of present in classical statistical physics, for example. So it's not so much conceptually new, and they go even further. So there is a bunch of people that tries to, let's say, redefine quantum mechanics purely by statistical, but kind of framework of statistical physics or classical statistical physics, but using the concept of a kind of curvy manifolds and so on, so on. So
good. Yeah, okay, I get the idea. So I, you know, I think I might, if I'm understanding it right, lump this model in with, you know, some stuff that's been done by Adler and like you know Rob Speckins, stuff like this. There's this kind of family of work that says, oh hey, look, you might have thought that this like feature of quantum mechanics can't be captured by purely classical theory, but whoa, like check it out, it can, right? So I think the way that these I think these theories are intended to be useful either thought experiments or proofs of concept to kind of, they do a couple things. I mean, one thing is they cultivate in us greater understanding of quantum mechanics because they're teaching us which things are characteristically quantum and which things aren't characteristically quantum, right? Or, can be reproduced by classical physics. And that's a way to kind of put us in a position of having a better grasp on what quantum mechanics is saying. So in that sense, right, they're useful toy models. They're useful as thought experiments because of the analogies that they bear to quantum mechanics. So again, I would say that's a sign that probably the virtue epistemic framework should apply to the interpretation of these theories, because their purpose is to be analogous to quantum mechanics in some ways and to be analogous to classical mechanics in other ways, perhaps, right? Another thing that might be going on, and I think this is kind of, this is clear from like what Adler does, for example, is that, he treats a theory like that as a proof of concept for the possibility of a more basic theory that has classical laws but reproduces the predictions of quantum mechanics, right? And you see some stuff like this from 't Hooft, as well, right? There's this kind of family of work that's like, hey, in these kind of special cases, I can reproduce quantum behavior with classical systems, deterministic systems, stuff like that. So, this is a sign that this is possible in a more developed theory, right? So yeah, I would say that's the place that these would fit within my framework. And then I would think that you would tend to apply the norms of the virtue epistemic means of interpretation.
Well, I would say there is a kind of seminar by Jarek Duda about quantum mechanics foundations and nature of time. So I can, and there's a lot of community that tries to present a kind of alternative concepts for explaining the quantum mechanics, but is faced with a kind of barrier in acceptance of paper even for consideration. So would your scheme somehow be helpful for a kind of alternative kind of views in a sense? Because well,
yeah, I mean, that's a tough problem in the sociology of science, right? So I mean, if my views are widely accepted, then perhaps, but of course, like I'm one guy in a philosophy department, so I wouldn't have too much optimism about my chances of influencing the broader physics community, except maybe quite some time down the road.
Okay, thank you for answering. Thank you.
Thanks so much. Noel, you're next.
Thanks. So I guess I want to go back to Jacob's question and maybe put a little bit of pressure, Dave, on the thought that like what we should do with ADF-CFT is something like the virtue epistemic approach. And this is a kind of veiled way of asking about whether or not there's at least like one other potential option on the table. So to set this up, right, here's a whole nother type of thing we might use toy models for. We might use them as part of constructing explanations, right? We're interested in sort of counterfactual dependency relations, or maybe counternomic dependency relations, or counter-metanomic dependency relations. And to figure out how these things all hang together, we have to consider other theories that differ from what we think might be the actual one in various ways, right? It's essentially like this sort of armchair physicist version of like intervening and wiggling variables in a, interventionist type experiment. For that kind of purpose, it's not clear that what we should do is take something like the physicist's partial interpretation and then proceed to bring out all of the normal kind of interpretive, Occamist norms and things like that, symmetry norms, et cetera. Exactly what we should be doing is, I think, not totally clear, but here's kind of a weird stab in one direction, right? Think like Lewis for a second. So you're interested in patterns of counterfactual dependence, and important to determining patterns of counterfactual dependence, there's the notion of overall similarity. So now there's a powerful, so suppose you're interested in like looking at counterfactual physics in order to help trace out explanations in your actual physics. you might think that it sort of constraint now on the interpretation of your toy models is something like maximal similarity to the actual world. And that might pull very, very differently than applying a symmetry argument to the theory sort of treated on its own terms.
Yeah, that's a nice point. Definitely. No, I really like the point. And I think, I mean, good. So good. Did you have more?
Yeah, I was trying to think of like specific examples. But like one that comes to mind is like the role of like universal force versus curved space versions of Newtonian gravity. Like if you just take the theory on its own terms, it's not clear to me that you should prefer one or the other on sort of standard kind of virtue epistemic interpretations. But if what you want to do is trace out certain counterfactual chains of dependence and explain stuff in GR, it seems like you should prefer the curved space-time version, quite plausibly. And I think the thought is that when we use toy theories in explanations like this, we typically have in mind some like space of theories or space of models that share certain similarities. And quite often the toy theories are like very extreme idealized points in this space. And given that, if we interpret them like on their own, we would tend to, if applying the standard interpretive tools, get rid of way too much structure, when in fact they have all the structure that like you can't see because all of these other forces are turned off, or these fields are, you know, non-interacting or what have you.
Yeah. I mean, all of that seems exactly correct, Noel, and very, very astute. So I think that a lot of what you're talking about is what I was thinking of as being kind of like put into the initial fixed partial interpretation of the theory that we're interpreting by the virtue epistemic framework, right? And it might be that for some purposes, similarity to real world quantities is going to be such a strong desideratum that what I'm calling that initial fixed partial interpretation is going to be very strictly specified to start out with. And there's not going to be much room to kind of like construct interpretations of the theory that, you know, disagree with each other and are still compatible with that initial, you know, fixed partial interpretation. Because remember, right, so the initial fixed partial interpretation kind of comes from the physicist's intentions in the sense of like which real world things or which things from the next theory that they're looking for are something is this theory supposed to be analogous to. And if the next theory they're looking for is something that's as kind of like ill understood and amorphous as M theory or something, then there's going to be like the fixed partial interpretation might be quite unspecified because, you know, we're not sure what analogies a toy model is supposed to bear to that theory. And I think that's kind of what's going on in these like, you know, these toy quantum gravity models, right? On the other hand, right, we might be wanting to do something exactly what you're talking about, where we treat, you know, Newton-Cartan theory as analogous to general relativity, and we ask some things about like, well, what's really different relativistically versus non-relativistically, right? And yeah, in that kind of situation, it might just be that the intentions that they bring to the table in asking that question are like, give this thing an initial fixed partial interpretation that's as close as possible to general relativity, you know, while being different and being non-relativistic, right? And so there'd be very little room for theoretical virtues to apply to the question of interpretation in that case. And yeah, indeed, right, you might, yeah, a thing that I probably should have flagged is that there's no contradiction with the virtue epistemic approach to suppose that the initial partial interpretation might include things that aren't invariant under the symmetries, right? It could. Like, it seems to me like in most the kind of things that people are doing in thought experiments and proof of concept, it doesn't have that feature, but it could, right? And then it would be much more like the quasi-epistemic way of doing things in that sense. So yeah. Yeah, I mean, I think I just have to say, like, you're absolutely right that cases like that can be interesting, and like, you know, that you're right about the norms that would govern them. And yeah, like I think you're just right. And whether one wants to see, I mean, one could see it as like a fourth piece of the taxonomy, or I think I would still want to say that the virtue epistemic approach applies in the sense that if you do have questions that aren't answered by analogy to the theory that you're trying to treat the toy model as analogous to, then you would probably want to answer those questions, you know, in some way if they come up. And then you would presumably use the method of saying, well, like, what's the kind of most plausible or most reasonable, which is really what I mean by kind of theoretical virtues, right? What's the most kind of plausible interpretation of the theory that has the features you're looking for? And so it might still come up in a few kind of like in a few of the details, but you're right that like in that kind of case that you're talking about, what I'm calling the initial partial interpretation is where all the action is almost.
Yeah, we can talk about this more. I'm worried that too much is being loaded onto the initial partial interpretation, but
Yeah, I haven't talked at all about what are the norms. I mean, except for gesturing vaguely at like the intentions of the people who are asking the question, right? I haven't talked about what are the norms on constructing that initial partial interpretation. And that could be very non-trivial in some cases. And so like, yeah, I think what you're pointing to are a class of examples where it is non-trivial, and further work would be needed to say, what are the norms that apply to those?
Great, thanks, Noel. Josh, please go ahead.
Cool. Thanks so much for the talk, Dave. This is kind of a meta question that's probably outside the scope of the talk, but I'm curious since the issue of virtues has come up so much. So in the virtue epistemic framework, which does seem to be, you know, a lot of what we're doing in philosophy of physics, and we're talking about norms, what do you take the status of these virtues to be? Like if I have two philosophers of physics and they disagree about not only the proper virtues to focus on, but perhaps the right way to weight these virtues, do you think there's like a straightforward fact of the matter about which of these philosophers of physics has the most reasonable or most plausible grip on the theoretical virtues? Like I'm happy to grant that, you know, at the end of the day, there's a fixed way the world is. Ultimately, we're trying to, you know, many of us are trying to, you know, be right about the way the world is. But when we get into these debates about virtues and the norms we're following and the right norms to follow, what do you take to be the status of these kinds of concepts?
Yeah, I mean, I'm pretty objectivist myself about epistemic normativity, right? Like I think it's pretty implausible to suggest that there's nothing objectively wrong about, you know, somebody's thinking as long as they obey the probability calculus, or as long as they are a good Bayesian or something. Like those norms seem too weak to me to be the only objective epistemic norms. But I should hasten to add that by objective, I don't mean like the universe dribbles justification, like metaphysical justification onto some hypotheses and not others, right? You know, there's going to be some story about what it means for something to be, you know, like there has to be some true story about what it means for something to be correct, like the correct thing to believe. And that's going to apply to physics as well. And that's a super tough question. Like it just seems evident to me that you know, and I know I like like I know it doesn't seem that way to those with a kind of more voluntarist epistemic bent, which I know is kind of your like starting point. So but yeah, it just like yeah, I mean, I think that if I'm in dialogue with somebody who thinks that there are no such norms, there's very little for me to say. And I think that's pretty analogous to a situation where I'm in dialogue with somebody who thinks that there are no practical norms or very weak practical norms. You know, and I'm trying to convince them to like do the right thing in some sense. You know, I can try to convince you to do the right thing epistemically. And it's going to be very difficult to kind of bridge that gap between the less skeptical and the more skeptical views. But yeah, I would think like, I mean, I guess like in general, a way that I would urge people to think about all this though, is to think of it on analogy with practical normativity and ethics, right? So people are going to have rock bottom disagreements about epistemic values, and you know that's not zero evidence that there are no rock bottom epistemic values, but it doesn't establish to my satisfaction that there are no rock bottom epistemic values. And you know there's going to be a kind of analogous like process of people trying to figure out what the rock bottom epistemic values are. I think the two are really quite analogous. And you know, an answer I would give would be basically like, think about it the way you think about ethical disagreements.
Cool, thanks, Dave. I'm inclined to say that's a very helpful answer.
Thanks, Josh. Kevin?
So Dave, I just want to pick your brain about an issue. So suppose I give you a theory, not by giving you the mathematical formalism or something, but just by like laying out the ontology and the dynamical laws that govern that ontology. And you know, it could be like a particle theory or something like that. And suppose the laws of the theory that I specify are such that there couldn't be observers in this theory. Am I right in understanding that sort of the way you're using the phrase empirical content, such a theory would not have empirical content? Because there are various points, I think maybe I sort of lost track. There was a couple points during the talk where it sort of seemed like you sort of made this move from a theory not having room for observers to the theory not having empirical content. And so, you know, at least, you know, if I sort of, at least it seems to me like at some sort of intuitive level, if I sort of articulate a particle theory and specify various force dynamics governing the particles, that there is in some sense empirical content to the theory, even though there may be no place for observers, and there may be even no way of building measuring apparatuses or something like that. So I just wanted to, I have a follow-up depending on how you answer that question, but I just wanted to get a little bit clear about how you were thinking about empirical content.
Can I ask Kevin a question about your question, Kevin, first, if that's okay?
Sure.
What do you mean by empirical here?
Well, so in some sense, that's part of my question to Dave.
Because I feel like I would say that your theory by definition has ontological content, because you define the theory by specifying the ontology and the laws. So I guess I'm just confused about what empirical could mean separate from ontological.
Well, I think that, you know, in a particle theory, particles have positions, let's say, and those are the sorts of things that we think that, you know, were we to exist in such a world, we would be able to measure, but we don't exist in that world. So you might sort of think, well, that's, you know, the location of a particle is, you know, the locations of all the particles would be part of its empirical content, as opposed to postulates of the theory that even if were we to exist would be unobservable or theoretical or something like that.
So you're identifying things that are like hypothetical empirical things, right?
Yeah,
if there were observers, then they could see these things.
In some sense, and I mean, part of this question is motivated by just sort of von Frossen's discussion of like what it is to be observable, but maybe taken in a more modal sense.
Yeah, good. I mean, like, so, and and I think there's a way to make sense of that approach within the quasi-empirical framework that I talk about.
Yeah.
You know, like you say you pick the quasi-empirical variables on the basis of certain relationships that they bear to real world empirical quantities, right? As opposed to picking them by saying, in what way does this toy theory limit to or approximate a real world theory? Yeah, so that can fit within the framework. I mean, I will say though that, I mean, I guess as I think you've sensed, I have some opposition to that way of thinking about it, and I think that these kind of counterfactuals are fairly underspecified in a way that's like, you know, I think it's there probably will be answers to them in a given situation, but the answers are going to be parasitic on like other questions that I think are more important and foundational, like, is this theory intended to be treated as a limit or an approximation to a real life theory, right? Or has it been used that way in real life physics? Or you know, was it historically put forward with the I mean, a big one I think is, was it historically put forward with the intent and the false belief that it could be used to model observers, or that it belongs to a general framework that could be used to model observers, right? I mean, I think those are the kinds of factors that are going to, you know, just as a matter of like, you know, when you're asking about the evaluation of counterfactuals, right? Like, as a matter of linguistic fact, those are the kinds of things that are going to feature, I think, into the semantics for those counterfactuals and determine whether they're true or not. And they just seem to me to be evidently not especially interesting questions from the point of view of the interpretation of physics as I think of it. So like, I think there's that is to say, I think there's sense to be made of the kind of analogies between the quantities in like a pure classical particle theory, maybe where the particles just bounce off each other like billiard balls, and observables in the real world. You know, or like, I think there are facts to the matter if we want to ask the counterfactual question, like, what would I see if I were like plunked into that world, right? Like due to the kind of historical development of pure particle classical mechanics, I think there are answers to those counterfactuals, but I think they're pretty uninteresting answers, you know, when it comes to the kind of questions that I think we're really asking when we interpret physics.
So you don't think that's interesting. So you don't think that that thinking about it that way can be used to probe interpretive principles that are judgments of, I mean, I would have thought that like maybe one of the key uses of thinking about it that way was as a way that was the sort of thought experiment way, where you're sort of the aim is to sort of think through what sorts of principles seem you know to operate implicitly in our interpretive judgments and so forth. It might be a way of sort of, you know, screening off the complexities of modern physics to consider these sorts of other scenarios. I guess I think the question's more interesting for that reason maybe than you do.
Well, I think there's something in the vicinity that does have exactly or close to the feature that you're talking about, which is what norms would we apply to like Newtonian particle mechanics if, like, the people who came up with it, we didn't understand that it couldn't be used to model observers, and we falsely thought that it could be used to model observers,
right.
And like we just kind of like you know, we bracket the fact that the theory can't model observers and consider the like false hypothetical where we plunk ourselves into that world, right? And I think that's essentially a way of applying the quasi-empirical framework, where we're talking about a kind of amorphous, like more basic theory than the theories that we're interpreting, which again is the thing that I think, you know, to use my earlier term, the right thinking Newtonian would be saying about you know, the Newtonian forces that we actually had kind of formulated at the time.
Yeah, I mean, just to put a cap on that, I think that I think probably something like that was what I had in mind when
Nice.
when I was talking about empirical adequacy,
Good.
where we sort of screen off. We're not interested in the question of whether or not it's true, and set aside the fact that we know the theory is false. So I now want to sort of put myself more in the sort of I forget what you were calling it, the quasi.
Yeah, quasi-empirical. Yeah. Okay, good. Well,
Yeah.
we'll have some. We'll exchange some emails about this because I want to make sure that like I want to make sure that I'm representing your views properly in the kind of written version of this stuff. But thank you. It's really helpful. Really helpful.
Thanks, Kevin. So we've got 5 minutes left. I have two more hands. I have Logan and then Alyssa again. So Logan, please go ahead.
Yeah, thanks. I'm struck by, it seems like both the virtue epistemic and quasi-empirical frameworks rely on some sort of intertheoretic relationship between this toy theory and some, we don't have a full theory of the real world in a sense, but some imagined theory of the real world. But I wonder to what extent perhaps these two models can help us interrogate the relationships between theories. In other words, maybe in some cases, a virtue epistemic is sort of a more natural framework for thinking about the relationship between one toy theory and some other theory. Given that in some sense they're all toy theories, right? It's toy theories all the way down, perhaps. And I'm wondering about, could we kind of reverse the framework and use, ask questions about, well, what seems more natural as an interpretation, and can that tell us something about the relationship between, different levels of theory or different levels of abstraction?
Yeah, right. I mean, I think that given that, as I was kind of alluding to before, approximate truth and inner theoretic relationships between theories that commit idealizations in certain ways and theories that commit fewer idealizations, like given how tough it is to understand these things in a kind of formal way, and yet how fairly good we are at understanding them in an intuitive way, I think it must be that stuff like this is kind of what's going on in the background when we do when we do this in practice, by which I mean not just scientific practice, but the practice of thought experiment and interpretation, right? So I think it's right that the norms that we might implicitly be following when we do that stuff should be a guide to doing things like maybe formalizing approximate truth in a more satisfactory way, or setting down criteria for what counts as a good reduction of one thing to another, right? So I think that it can totally go both ways in that sense. And it seems like it might be actually that going in that direction will be the more informative direction that might lead to bigger breakthroughs potentially.
Thanks, Logan. All right, Alyssa, I think you have the last question.
Okay. I wanted to come back to what you were saying about Belot. So you're disagreeing with him though, because you're saying that there aren't these relative distances, there aren't these relative distances in these theories with these symmetries. Is that right?
Yeah, I guess the way to put it is there are two things he could be asking when he puts forward those examples. One of them is what is the right way to interpret these models on the quasi-epistemic or the quasi-empirical framework, and one of them is how do we interpret them on the virtue epistemic framework. And once you prize those two apart, then the answer is on the quasi-epistemic framework, don't mod out the symmetries, but that's not surprising and shouldn't be a problem for the symmetry to reality inference fan like myself. And on the other side, the answer is do mod out the symmetries, and this isn't a reductio ad absurdum at all.
Well, that's the part I didn't get, because throughout, at a certain point, you were no, I thought you were assuming he was interpreting it, in this second way, in the virtue epistemic way. And then in that case, you get the conclusion that, yeah, you don't have these relative distances. And I thought he was saying like, that can't be a way to interpret this theory. So, I mean, on your view, he is making a mistake there. And I feel like, I don't know, I don't think he's here. I feel like he would push back on you and say, no, like there's something wrong with interpreting the theories in that kind of way. Is that wrong?
Yeah, I haven't. This is one of the few things in this that I haven't talked with him about yet, because like we talked about the chapter this is in, but this is a later addition to the, you know, in revisions. So I need to talk with him about this. Actually, I haven't yet. And I'll certainly let you know once I see what he has to say. But yeah, it might be that I am misunderstanding what he's up to in some way, and he does see what he's doing as kind of like something that should be seen as fitting within the quasi-empirical framework, or something that, like, you know, I haven't put my finger on yet.
Yeah.
I think that's entirely possible. But I think also a thing to keep in mind, right, is that his paper was addressing folks like a more radical younger version of myself that thought of symmetry to reality inference as an unbreakable rule of theory interpretation, right? And in that sense, like, you know, I should perhaps be more fair to him in the sense of saying, like, he's exactly right. It's not an unbreakable rule. And, you know, that kind of case can be understood as one in which we're looking at an exception to it if we're talking about the quasi-empirical approach, which is like an approach to interpreting theories. So like, if symmetry to reality inference doesn't always work in that approach, it is a counterexample, right?
Okay.
Totally. And so in that sense, like, yeah, maybe I should have kind of front loaded that that caveat to what I was saying a bit more.
I'm sorry to have to cut you off here, but we are at the hour and I want to make sure people are able to get to their next appointments. But I want to thank everybody for your amazing questions. And of course, Dave, for an unbelievable talk and discussion. And that's it. So next seminar in 2 weeks is going to be Alex Meehan, who's here right now. We'll be talking about Bayesian epistemology in quantum mechanics in a quantum world. So stay tuned. There'll be an announcement soon. But thanks again, everybody, and have a great week.
Everybody enjoy your next appointments.